The density of air is its mass per unit volume. This means a volume of air at high density has a higher mass than the same volume at low density. And if there is a larger mass of air, it will contain proportionally more oxygen. The density of air in the atmosphere changes at different temperatures and altitudes. That means the air that enters an engine at different locations could have very different amounts of oxygen. The amount of oxygen in air directly affects how well it supports combustion, so it can be important in determining an air-fuel ratio for an engine. Ground is a term used to indicate connecting a component to the vehicle frame or chassis. Current flows from the positive terminal of the battery through a controlling device such as a switch, then through the component. The return path is through the vehicle chassis or frame to complete the circuit and allow the component to operate. Using the vehicle frame in this way simplifies the circuit wiring. A potentiometer is a mechanically variable resistor which, in EFI applications, is normally a film type. It can be linear or circular in construction and has 3 electrical connecting points. 2 are at the ends of the resistor and the third is attached to a center sliding contact, arranged to move across the resistor. A reference voltage is applied to the resistor so that a steady current flows through it. As the center sliding contact moves across the resistor, it measures the voltage at the point it is in contact with, and provides a reference voltage for that position. In automotive applications, the circular form is commonly used as a throttle position sensor, with the center contact attached to the throttle plate. The throttle plate position can then be monitored by the control unit. Pressure and vacuum are terms in everyday use in the automotive industry. Manufacturers recommend a pressure to which tires need to be inflated, and manifold vacuum is used to operate a brake booster. Gases exert pressure on all bodies they make contact with. This applies also to the air in Earth's atmosphere. Air has mass, and as a result it exerts pressure, called atmospheric pressure, not only on the Earth's surface, but also on all objects on the Earth's surface. Atmospheric pressure varies with altitude, but at sea level it is calculated as 101.3 kilonewtons per square metre, or 101.3 kilopascals. But if this is so, why does a pressure gauge read 0 when it is not in use? This is because the gauge indicates pressure above atmospheric pressure only. This reading is called gauge pressure. If absolute pressure was needed, an absolute pressure gauge would be needed, and it would read 101.3 kilopascals when not in use. Absolute pressure equals gauge pressure plus atmospheric pressure. Readings on an oil pressure gauge or on a tire gauge should really have 101.3 kilopascals added to them. It is normal practice, however, for the gauge reading alone to be taken as the accepted value. If pressure being measured is below atmospheric, a pressure gauge with its 0 reading is of no value. This is why, for pressures below atmospheric, as in a manifold vacuum or depression, a vacuum gauge is normally used. In a petrol engine, the position of the throttle plate controls the volume of air, or air-fuel mixture, entering the manifold. At idle speed, the pistons draw air away from the manifold at a faster rate than it can pass the throttle plate into the manifold. A high vacuum, or a depression, exists. At wide open throttle, depending on load, the vacuum is much less, and pressure in the manifold rises, closer to atmospheric. A vacuum gauge can be calibrated in millimeters of mercury, and the scale reads from 0 to 760. The scale is derived from the fact that atmospheric pressure supports a column of mercury 760 millimeters high. This glass tube, closed at one end, is filled with mercury, then inverted in a bowl of mercury. The column of mercury in the tube falls to about 760 millimeters. The space above the mercury is a vacuum, and the atmospheric pressure on the exposed surface of the mercury supports the column. At sea level, atmospheric pressure supports a column of mercury 760 millimeters. But at higher altitude, its height falls, which indicates that atmospheric pressure at that altitude is less. A scale of 0 to 760 millimeters can thus be used to indicate the degree of vacuum or depression that exists below atmospheric pressure. At idle speeds, a vacuum gauge connected to the intake manifold will indicate a reading of approximately 450 to 500 millimeters of mercury, depending on altitude. Some engine management systems signal changes in atmospheric pressure by using a barometric pressure sensor in the ECU. This is because, above sea level, air pressure is reduced. So to maintain correct air-fuel ratio, a vehicle has to reduce the amount of fuel delivered to the engine. The term stoichiometric ratio describes the chemically correct air-fuel ratio necessary to achieve complete combustion of the fuel. It is represented by the Greek letter lambda. The value of the ratio is 14.7 parts of air to 1 part of fuel. By mass, that's 14.7 kilograms of air to each kilogram of fuel. So if lambda equals 1, the air-fuel mixture is at the stoichiometric ratio of 14.7 to 1. If an air-fuel mixture has a higher figure, say 1.03, there is more air in proportion to the fuel than 14.7 to 1, and the mixture is slightly lean. A mixture with a lower lambda value has less air, proportionately, than fuel, and the mixture is slightly rich. The exhaust gas oxygen sensor is also called the lambda sensor, since it can be used to maintain the air-fuel ratio at lambda equal to 1, within very close limits. It can be installed in the exhaust manifold, where it measures the percentage of oxygen in the exhaust gases. A high percentage of oxygen may mean too little fuel is entering the engine, the mixture is too lean, and the lambda is greater than 1. The sensor delivers this information to the ECU, which adjusts the mixture accordingly. Similarly, a low percentage of oxygen may indicate too much fuel is entering the engine, the mixture is too rich, and the lambda is less than 1. A tachometer is used to indicate engine RPM. It is normally connected to the negative terminal of the ignition coil. The pulses from the ignition primary circuit are then used as an input to operate the tachometer. At idle speed, the frequency of the pulse is steady. As the engine speed rises, the frequency of the pulse increases as the tachometer indicates. A tachometric relay uses the same input from the negative side of the ignition coil to ensure the relay operates only when the engine speed is above a specified minimum, say 350 RPM. In this case, it operates as a safety device, ensuring the fuel pump operates only when the engine speed exceeds this figure. Volumetric efficiency compares the volume of air entering a cylinder during intake to the internal volume of the cylinder when the piston is at bottom dead center. It is usually expressed as a percentage. In a naturally aspirated engine, one without forced induction, volumetric efficiency can never be 100%. This is because of the resistance to the airflow that occurs at the carburetor, manifold, and the intake valve. With forced induction, the incoming air is compressed so that a greater volume and mass of air is forced into the cylinder during the intake stroke. That takes the volumetric efficiency to above 100%.
This section examines the air supply. In multi-point injection systems, the air required for the combustion of the fuel is led from the air filter through the throttle valve and into the common manifold or plenum chamber. From here, individual intake runners or pipes branch off to each cylinder. All of these pipes are of equal length. The design of the intake system determines how large an air mass can be drawn into a cylinder at any given engine RPM. This is where most advantage can be taken of electronic fuel injection, since it can achieve exactly uniform distribution of the air delivered to the cylinders. With unobstructed passages to each cylinder, the cylinder fills with air as efficiently as possible. The breathing of the engine, or its volumetric efficiency, is improved. The more air crammed into the cylinder, the denser the air-fuel mixture when ignition occurs. This increases the thrust on the piston and increases engine power output too. The temperature of the air influences how dense the air-fuel mixture will be. Cold air is denser than hot air, so it has a greater mass in any given volume. This is why on most intake systems the air entry to the intake is away from engine heat, to ensure the entry of cool air. Since the manifold carries air only, it doesn't need to be heated by coolant. Filtered air arrives at the intake port as cold and dense as possible, ready for mixing with the fuel from the injector. How petrol burns must be controlled. If it burns too quickly, it can cause detonation, sometimes called ping or knock. So special additives are used to slow down the rate of combustion. Octane rating is a measure of how well a petrol resists detonation. The higher the rating, the less likely it is that detonation will occur. Higher operating pressures in the combustion chamber can also cause abnormal combustion. A lead-based anti-knock additive used in leaded petrol can allow these higher pressures without loss of performance. Lead additives are also lubricants. In high compression engines, lead compounds coat valve faces and seats and help prevent wear. Leaded petrol is used in older cars that have few or no emission controls. It should never be used in engines designed for unleaded fuel. Governments now limit levels of lead in petrol, and unleaded petrol is replacing leaded petrol. So-called unleaded petrol may contain small amounts of lead, but maximum levels are tightly controlled. For petrol to burn properly, it must be mixed with the right amount of air. For a petrol engine, the air-fuel ratio by mass is about 15:1. By volume, it's about 11,000:1. Not much petrol, but lots of air. A lean air-fuel mixture has more air in proportion to the amount of fuel. A slightly lean mixture gives good fuel economy and low exhaust emissions, suitable for cruising conditions. A mixture that's too lean can make an engine run roughly and overheat. A rich air-fuel mixture has less air in proportion to the amount of fuel. A slightly rich mixture can produce more power at lower temperatures, but the extra fuel it uses steps up fuel consumption and emissions. A too rich mixture fouls spark plugs and causes incomplete burning, and that reduces power. In normal combustion, the spark plug ignites the mixture and a small ball of flame forms around the tip of the plug. The piston compresses the mixture, the flame spreads faster and moves evenly to halfway through the mixture. The piston reaches top dead center. The flame picks up more speed, then shoots out to consume the rest of the mixture. Combustion ends with the piston a short way down the cylinder. Detonation is a violent collision of flame fronts in the cylinder caused by uncontrolled combustion. It occurs after the spark plug has fired. The sudden rise in pressure can cause a knocking sound. Sustained detonations can lift temperatures enough to cause pre-ignition, also called auto-ignition. Pre-ignition occurs before normal combustion, when something in the combustion chamber heats up enough to ignite the mixture before the spark plug fires. A mixture may also ignite simply because it is unstable under the higher heat and pressure. Detonation and pre-ignition can cause severe damage and must be avoided. Engine management systems use knock sensors to detect detonation, and they retard ignition to stop it. This section examines basic principles of electronic fuel injection. Because of the need to comply with exhaust emission regulations, the modern petrol engine requires a fuel system of extreme accuracy and long-term reliability. A correctly matched air-fuel ratio must be available at all times and under all conditions. This is satisfactorily achieved by electronic fuel injection. EFI is a pressurized indirect injection system that uses solenoid-operated injectors with a fixed orifice. When they're energized, fuel passes through the injector body. This arrangement is called a multi-point system. One injector is located in each intake manifold runner or pipe adjacent to each cylinder. An electronic control unit, or ECU, opens the injectors by pulsing their electrical current. They spray fuel into each intake port directly in front of each intake valve. Fuel leaving the nozzle is atomized, and it mixes with the air also entering the system to form a combustible mixture. Fuel pressure is kept at a constant value above manifold pressure, so that the amount of fuel injected is determined only by the length of time the injector is held open by the ECU. This is called the pulse width of the injector. The triggering signal to operate the injectors can be supplied from the ignition system or from crank angle sensors on the crankshaft or the camshaft. Engine fuel requirements change according to engine speed, load, and temperature, so the ECU needs information on these changes. Sensors measure these variables, then relay the information to the ECU in the form of electrical signals. The ECU then calculates the duration of pulses necessary to provide the fuel required. Extra fuel required during cold starting can be supplied by increasing the number of injection pulses, or by fitting a separate cold start injector that operates independently of the main injectors when the engine is cranking. The throttle body injection system, also called a central fuel injection system, has a single injector, or in some cases 2 injectors, mounted in a carburetor-like throttle body. The throttle body assembly is fitted to the flange of the intake manifold, and the fuel is sprayed into the intake air entering the manifold. The air-fuel mixture is then carried through the manifold into the engine. Fuel pressure is maintained at a constant value, and an ECU pulses the injector or injectors. This section examines petrol fuel. Petroleum or crude oil is taken out of the ground as a mix of impurities and highly flammable compounds of hydrogen and carbon, called hydrocarbons. It is processed into many products, including petrol and diesel fuel. Petrol is used in different forms in different engines. It is very volatile, mixing easily with air to form gas or vapour. The more effectively liquid petrol is changed into vapour, the more efficiently it burns in the engine, so high volatility is desirable.